In the last class, I missed on discussing a very interesting area. When I was talking about units and measurements, I must talk about Kelvin and the triple point. You should know about this. So if you look into your book or any standard textbook, the definition of Kelvin, which is the SI unit of thermodynamic temperature, goes as follows. The Kelvin is the fraction 1 by 273.16 of the thermodynamic temperature of the triple point of water. So that is how the Kelvin is defined. It's the 1 by 273.16th fraction of the thermodynamic temperature that water has at its triple point. Now what does this triple point mean? And it is for that purpose that I am recording this particular class. So if you look into this curve, what have we got here? On this axis, this is the pressure. The same pressure, force by area, which you have been studying, and in the units that are used here is atmosphere. And in this axis, in the horizontal axis, we have temperature in the units of degrees Celsius. And what is this curve? Well, this is it's called the phase diagram of water. The phase diagram, in this case, of water, H2. You can have phase diagrams for CO2, for ethane, for ethyl alcohol, and a lot of substance. Each and every substance, when you represent it in this manner of pressure versus temperature curve, that's a phase diagram. So from this phase diagram, we get to see 1, 2, 3 curves. So this violet part here, that's one curve. This is another curve which is named the freezing curve, and this is another curve which is named the boiling curve. And somewhere here is the 100 degrees Celsius temperature, which is the boiling point of water. Somewhere here is the freezing point of water, and this is the normal 1 atmospheric pressure that we on Earth experience. What is triple point of water? The triple point of water is this point at which the temperature is 0.01 degrees Celsius and the atmospheric pressure is 4.5 millimeters of mercury. If you remember, actually the 1 atmospheric pressure with which we are accustomed is 760 mm of mercury in a barometer. If you place the tube with the mercury filled in it, it will rise up to a height of 760 mm. So as you can see in the triple point, the pressure is pretty low, 4.58 mm, and so is this temperature. These are the temperature and pressure coordinates or values for the triple point of water. What does triple point mean? Triple point, as you can understand from the word triple, is basically that particular pressure and temperature at which all the 3 states of matter for that substance coexist simultaneously. So triple point in case of water, at this temperature and at this pressure, the 3 states of water, that is ice, the water as we call it, the liquid state, and gas state, that is vapor, exist simultaneously. So if you have a container in which you take some water and in some manner you take the temperature and pressure of that container of water to this value, you shall get ice, steam and water all in together. That is the triple point meaning, and that's very fascinating. As you can see here, that in generally, since on Earth the average temperature lies somewhere around 20 degrees Celsius and the average pressure is the 1 atmospheric pressure, so that corresponds to a coordinate here. So therefore water is mostly in the liquid state on Earth. By the way, I forgot mentioning this, that this area to the left of the freezing curve, that is this area, for these values of temperature and for these values of pressure, water will exist as ice. The boiling curve, that is on this portion, that is on this area, water will exist as the vapor or the gaseous state. And it is in this particular area, the golden zone, in which water exists as the liquid state between 0 degree and 100 degrees Celsius, and between this pressure here, the exact value of the pressure I've forgotten it for the moment, and between this and this pressure. And it is because that water can exist in this particular temperature and pressure, and because water is present in the liquid state here on Earth, that we have life here on Earth. So that's another significant area for this. Anyway, so this is all about the triple point of water. And therefore when you read the definition of Kelvin, and it says that it is defined as 1 divided by 273.16 the temperature of the triple point of water, that means atom, times 0.01 degrees Celsius. Obviously you have to convert this to Kelvin. That is the definition of 1 Kelvin. In the last class we were talking about the ideas of measurement. I was discussing with you that why and how measurement is so integral to this subject of physics. Here I want to share a funny story with you. It's actually in Bengali. In Bengali we often hear our grandfather, fathers, or the people of the previous older generations, they often say in Bengali, like after taking a heavy meal during their lunch, after eating delicious foods in their lunch, they often say this, যে এবার একটু লম্বা হওয়ার সময়, যাই গিয়ে একটু লম্বা হই, which basically means that let me just go and lay on the bed, let's take a small nap. So in Bengali they often say যাই একটু লম্বা হই. But do you know that this actually is true? What I am saying is that when you are lying down on a bed, whenever you are sleeping, or for that person matter, even if you are not sleeping, simply lying, you are taller than when you were standing. If you accurately measure from your head to your toe, you will find that compared to when you are standing, just like I am standing right now, when you are sleeping you are about 2.5 centimeter or 1 inch taller when you are lying down. That's true, because when you lie down, what happens is that if this is like the bones of your spinal cord, in between the bones in these areas you have got the cerebrospinal fluid. So when I am standing like this, that cerebrospinal fluid gets compressed. As a result, I become 1 inch shorter. But when I lie down, it gets expanded, and as a result I become 1 inch taller. And this is very much true when the suits for the astronauts are made who go and travel outside into space. These considerations are made because in space the gravity is so less. It's almost a zero gravity situation that this cerebrospinal fluid, it expands, and as a result that consideration has to be taken into account. During the initial Apollo missions to the moon, astronauts often complained that their suits felt tighter when they went out into space, because the suits were made by taking their height and weight measurements here on Earth, and out there they slightly increased in their height. As a result, the suits did not match with their body. So even during fun, when a lot of people say this kind of things, which we think are simply some old proverbs and adages of the previous generations, well, we see they do have scientific meanings. Now if we are talking about the measurement, there is no better way than to finish it with time. Measurement of time. Now, do you know what are the certain best timekeepers in this entire universe? Like we measure time with the help of a clock. So for us the clock is a timekeeper. But for the universe, what is the best form of timekeeper? The best form of timekeepers is something known as pulsars. So pulsars, what are pulsars? Pulsars are rotating neutron stars. Neutron stars, that is stars which are entirely made up of neutrons, packed neutrons, and when they rotate rapidly, those rotating neutron stars are called pulsars. And these pulsars, they whiz out radiation like this, those rotating pulsars. Actually these neutron stars are heavily dense. Like if you were to go near a neutron star and take a spoon with you, and suppose you take a teaspoon of neutron star, that teaspoon of neutron star will be equal in weight to the entire city of Kolkata. Just to give you a perspective how dense neutron stars are. But these neutron stars, they are excellent timekeepers. I give you an example. This is of the pulsar PSR. You can look up in the net. It's PSR 1937 plus 21. This is the code of the pulsar and the time. This is the time period of that pulsar. You can look up into the net. This is the code of the pulsar. That's how astronomers name them. This pulsar has a time period of 1.55780644887275 plus minus 3. This 3 is for this last decimal place. Milliseconds. That's how precise these pulsars are. Just look at the number of decimal places. 3, 6, 9, 12, 14. So you know the time period of this pulsar up to 14 decimal places. So they are the excellent timekeepers of the universe. But what about time here on Earth? Can we human beings really measure time? Are we capable of measuring time? When you look at a clock and the hour hand of the clock moves by one room, the 1/12th of the entire degrees in the clock, you say 1 hour has passed. So what is the clock basically? So if this is a clock, so this is 12 and 6, this is 9 and 3, you have 1, 2, 5, 4, 7, 8, 10, 11. So how do we say 1 hour has passed? When the hour hand moves from here to here. So it completes this angle theta. What is this angle theta? It is 360 degree by 12. 360 degree is the entire angle of the circle and 12 is the number of divisions. So every time the hour hand moves or has an angular displacement of 30 degree, we say an hour has passed. Right? That's how we measure time in our home. What about when you're outside? Suppose you have gone somewhere and from your home your guardian calls you and asks where you are. And you say, well, I am 15 minutes away from my home. So when you say this, 15 minutes away from your home, what do you actually mean? It basically means like you have visited that place before. Say that place is 3 kilometers away from your home. And each time when you return from that place, you found that it took you around 15 minutes. It may be 14, it may be 16, but around 15 minutes to return back home. So conveniently, instead of telling your guardian that I am 3 kilometers away from your home, what do you say? I am 15 minutes away from your home. Or I am 15 minutes, within 15 minutes I will arrive. And it's not just the case for you, we all do this. We often interchange the units of distance and time so conveniently in our daily life. It's ingrained in our daily life. We often misinterpret distance for time. Actually, when we are saying that we are 15 minutes away from the home, what we are meaning is that we are 3 kilometers away from the home, and I know that it will take me 15 minutes to cover this 3 kilometer distance. Similarly, when I say about the time in the clock, what you are basically saying is how much angle the hour hand has moved. And since you are watching the clock from your childhood and you have never thought about this angular displacements before, all you think is that when the hour hand moves this particular distance, that's 1 hour. But even actually this is also a movement of a distance. Actually the hour hand is completing this part of the circumference of the circle. The entire circumference is 2 pi r and the hour hand is completing 1/12th of that circumference. So basically it's pi into radius of the clock by 6. This is the amount of distance in meters that the hour hand is completing and which you are saying as 1 hour. So basically we do not have much idea of time. We cannot measure time. All we measure is time intervals. If you say that I started studying at 9 p.m. and I got up at 10 p.m., what you are measuring is time intervals, a 1 hour time interval. How can you be so sure that this is 9 p.m.? What is 9 p.m. for you in some other country, in some other time zone, that may be 5 p.m. or 5 a.m. So time is another relative concept. Ask this question to yourself, do we actually measure time or do we just measure distances and then convert them into the convenient units of time with which we are familiar. Even this 365 days in a year, which we say is to be the unit of time, don't you think that is the unit of distance? Don't you think 365 days is actually the time that the earth takes in moving around the sun? And since we know this distance and the speed of the earth to such accuracy, we can conveniently find out that this time is equal to 365 days, and thus we say we have measured the time. What we have actually measured is the circumference and the velocity.